Hello, welcome back. So in this part, now in the step 11, we will design shear reinforcement because now we know that tau c value is less than tau v, which means concrete alone is not sufficient for the shear resistance. We have to provide extra reinforcement as shear reinforcement to take care of the diagonal tension criteria. Okay, so in the design of shear reinforcement, first we have to find out maximum shear force. This we have already calculated in the previous step. And now we know that shear force taken by concrete, we represent this as VC. And the formula for the VC will be tau C into B into D. So tau C is the permissible shear stress for the concrete without shear reinforcement multiplied by area of cross section. So this is how we find out how much shear force is being taken care of by concrete. So this much shear force is taken care of by concrete alone, and this is the total shear force. Okay, so now the remaining part of the shear force, we have to provide reinforcement to take care of the remaining part of the shear force. So how much shear force is to be resisted, that we will find out. So this is the design shear force for which we have to design shear reinforcement. So V is the total shear force, VC is the shear force resisted by the concrete. Now putting the value, we can easily calculate the design shear force. So this is the shear force for which we have to design the shear reinforcement. So now we can we have already provided bent up bars to resist the shear force. So first we will find out the contribution of the bent up bar, and then we will find out the we will find out how much stirrups is to be provided to resist this shear force. So first we will check the uh, bent up bar contribution. So shear force resisted by the bent up bar, we can find out this, we can use this relationship. I have already explained this relationship is given in the clause number B. It is given in the clause number B 5.4 of the IS code. So you can see this formula there, sigma SV into ASV into sine alpha. So in the ASV, there you can see sigma SV is the permissible stress in the steel, which is sigma SV is equivalent to sigma ST. Okay, so this is 230. Similarly, ASV is the cross-sectional area of the bent up bar. We are using two bent up bar, so 2 multiplied by area of cross-section of one bar will be this one. And at what angle these bent up bar are bent up? They are actually bent up at 45 degree. So the same formula is given there. So putting all the values, we can now find out the contribution of the bent up bar. So here you can see bent up bar can resist this much shear force to this much shear force can be resisted by the bent up bar. But in the IS code, in the clause B 5.4, IS code has mentioned that the contribution of the bent up bar cannot be more than Vs by 2. So now I will write here, it says here Vs dash, which is contribution of the bent up bar, should be less than or equals to the half of the shear force, design shear force, this one. So only half of this value can be resisted by bent up bar. Half value is to be designed for the vertical stirrups. So that is, you can see here, actual contribution is this one, but we are restricting this value to this one. This is what IS code has suggested. So we are, as per IS code recommendation, contribution of the bent up bars is now restricted to half of this value, which is 6695. So in our design, we will assume that only this much shear force will be resisted by the bent up bar. Now remaining part of the shear force, which is again half of this one, which is 6695, it will be resisted by the vertical stirrups. So now as I written here, shear force for which vertical stirrups are to be provided will be, now I am representing contribution of the shear force, contribution of the vertical stirrups for the shear force as Vs double dash. So Vs minus Vs dash is equals to 6695. So for the same contribution, we will provide vertical stirrups also. So now for vertical stirrups, first we have to assume the diameter of the stirrups. So we are assuming that we are using a 8 mm dia, two-legged vertical stirrups. So which means if stirrups is like this, so this is one leg and this is second leg, and the dia of this stirrup is 8 mm. Okay, so now the only thing that we have to find out in case of stirrups is the spacing, and we will find out spacing from four criteria as I have mentioned in the steps. So first we will find out spacing from this formula. So the same formula is given in B 5.4 clause of IS code. So you can, okay, I will show you that in the IS code also, so that it will be clear from where we got this formula. So there you can see this is the formula for vertical stirrups. So from this we can easily find out SV. So we can write SV is equals to sigma SV into ASV into D upon VS. As contribution of the vertical stirrups, we are representing this as VS double dash. So this VS double dash value is actually this one. Okay. So this is how we will find out spacing in our slide. So after putting all the values, there you can see these are the value we have put. Sigma SV is 230, ASV again, as I said, leg 1 and leg 2. So in this case, ASV will be 2 multiplied by pi by 4 into dia of stirrup, which is 8 square. So this is how we find out ASV. So there you can see I have put the value of ASV. Then D is the D provided. This is actually D provided. And VS dash dash it will be 6695. So by calculation, the value of the spacing is 176391. Similarly, we will find out minimum shear reinforcement spacing. So again, I will show you that in the IS code also. So this is the formula to calculate spacing from this criteria also. So we will find out spacing of the stirrups from this formula also, which is for the minimum shear reinforcement. So here you can see also SV is also present in this formula. So SV can be written here as ASV into 0.87 Fy upon 0.4 B. So from this formula, we can find out SV. So we will check that on the slide. So there you can see the same formula that I have written here from the page number 48. So putting all the values again here. So the spacing from the minimum shear reinforcement criteria is 245. So as per IS code, the spacing of the vertical stirrups should be the least of 4 points that I have explained in the steps also. So what are those? So as it is written here, spacing of vertical stirrups to be not greater than the least of. First, I will show you this criteria in the IS code. There you can see on page number 47, it says maximum spacing of shear reinforcement. So it says the maximum spacing of the shear reinforcement measured along the axis of the member shall not exceed 0.75 times of D for vertical stirrups and for inclined stirrups. So we are not using inclined stirrups, so we are not considering this. So for vertical stirrups, it should not be more than 0.75 D, or in no case it should not be more than 300 mm. And also now there are two criteria which we have taken from the IS code, which is one criteria is 0.75 times of D, which becomes A, Then second criteria becomes 300 mm. Third criteria, spacing by calculation. So by calculation, we have calculated spacing by calculation. And the fourth criteria is SV from minimum shear reinforcement criteria. So all four criteria is to be find out, and then we will see which one is giving us the minimum value, and that minimum value we will adopt as our spacing. So we have calculated all four things, and 0.75 times of D will be 0.75 multiplied by 511. So all these value I will check. I will show you that in the IS in the slide. So there are 300, then 0.75 times of D, then by calculation it is 1763, and from the minimum shear reinforcement criteria it is 245.12. So all four criteria is giving us some values of the spacing, but we will adopt the least value, which is 245. So we can say now again it is written as 245. Again we will round off this value to the multiple of the 10, and now the round off value will be on the lower side. So I will adopt this as 240. Why I am not taking on the higher side? Because if the spacing of the vertical stirrups, if I take them on the higher side, then it means if spacing is more, like you can see this is the beam and this is the reinforcement that we will provide vertical stirrups. So if the spacing between them is more, then number of vertical stirrups will be less, which is the required reinforcement. I mean, we are providing less than the required, so that is why we will always assume lower side. I mean, we will round off the value on the lower side. So that is the reason. So now we can adopt this value, and we will write here providing two-legged 8 mm dia vertical stirrups at 240 mm center to center. So this finish our design calculation for the singly reinforced beam. Now final step is about to make the sketch. So all the calculation that we have done, now we will show that in the sketch. So I will show that sketch to you. So the sketch of reinforcement, you can see here our beam, and all the values are given here 200, and there you can see the stirrups we have provided. So stirrups are 240 center to center, two-legged 8 mm dia. Similarly, bent up bars are, so these are actually two bars which are bent up. Here also, these are two bars which are bent up. And cross section at this point. So cross section at this point, you can see here, this is cross section 1-1. So there you can see this is cross section 1-1. So in the cross section 1-1, you can see 4 bars are there, and these two bars are actually a hanger bar. So they are not in our calculation. We just provide them so that our stirrup, which is the ring, it can hold up. Okay, so that is why we provide them. It is not included in our calculation. So we are providing 2 bars of 12 mm dia so that our stirrups can hold up. Okay, so in section 1-1, you can see 4 bars are there. Now in section 2-2, there actually this section is wrong. If we cut section here, in that case at this point there are 4 bars, and at this point there are 2 bars because 2 bars are bent up. So this is how we show the cross section of the bar, and also at the same time we do proper dimensioning and proper notations. Like these 2 bars are the hanger bar and 2 bars are the bent up. This one, these 2 bars are the bent up bar. So as I written here, 2 bars of 16 mm dia, and 6 dia we sometimes represent dia as hash. So hash value we represent for HYSD bar sometimes, and for MS bar we represent by 5. Okay, so if it is written as 16 dia 16.5, we can read this as 16 mm dia of MS bar, and for HYSD bar we can use this hash value. Okay, so this is the sketch that we have done, and also you can see the bent up bars are located at, so this is actually taken from the center, this center of the bearing. So this is actually L by 7, which is 750 mm. So bent up, I mean bars are bent up at 750 mm from, and similarly on this side also. And these are our stirrups. So I hope the sketch is clear to all of you. So this sketch is required to be made uh, after the calculation. So this finish our design problem. So I hope you understand the problem. Thank you. I have taken these references from these notes. Thank you.